Hello, welcome to this video 1-4A on limits and continuity. We're going to start getting into some calculus stuff, and we'll talk about when a graph is continuous. And so the beginning part of this is going to require knowledge of limits. That's the objective. Determine continuity of a function and limits at certain points of a function. So here we have the definition. It says, informally, a limit is a y value which a function approaches as x approaches some value. Okay, and it's written here, the limit of f of x as x approaches c is equal to L. Okay, so this means as x gets closer to the c value, okay, the output values, our y values, are going to approach L, whatever that may be. Okay, so and it's important too when we write a limit, right? We need to write it like this. So the limit as x approaches a value c of f of x is equal to some value L. Okay, so kind of the idea is that when we have a function, okay, and we'll look here at this example here, y equals f of x, you want to see, okay, what's the y value, what's the output at this value? So here, if we look at example 1, it says the limit as x approaches -4 of f of x is equal to, so if I look at -4, okay, my x value, which is here, okay, my function, as my function gets closer and closer to -4, what's this y value approaching? And it's approaching this y value of 1. Okay, so for a limit to exist, the left side has to be equal to the right side. Okay, so they need to come together. So we can test the other side. So I just look and ta-da, they both meet at that point, right? So the limit is equal to 1. Now we can also evaluate functions, and you guys are used to this, right? So number 8 says f of -4 is equal to. So I look at my function, and lo and behold, at -4, the output is 1. Okay, so notice they match, and that'll be important. We'll talk about continuity in a second. Okay, example 2, it says, what is the limit of f of x as x is approaching -1? Let me switch colors. Okay, so where's -1 is right here. Okay, so my function's getting closer and closer right there. And then on this side of the function, getting closer and closer to this. So the limit, the function is approaching that value, which is 4. Okay, now when I actually evaluate, when I plug in -1 into my function, notice that the output, or the actual value, is down here at 1. So notice that those don't match. Okay, that's important. We'll come back to that idea. Next example, example 3. What is the limit of f of x as x approaches 2? Okay, so here's 2. So here's my graph approaching 2. Okay, and on this side approaching 2. So that is 1. Okay, and then we'll look at example 10. What is f of 2? So if you look at f of 2, notice how we have a hole here. Okay, so there's no value of f of 2. So we can say this does not exist. DNE. Okay. Number 4, what is the limit of f of x as x approaches 3? Okay, so we'll look at 3. Okay, here's 3. Notice how there's a vertical asymptote here. Okay, so it's going down here. It's approaching -infinity. And on this side, approaching -infinity. So the limit as f of x approaches 3 is -infinity, but we're going to say it does not exist. DNE, does not exist. Okay, and then what is the actual value at f of 3? And the same idea here that it does not exist. Okay. All right, I think I'm like running out of colors. Oh no, I got this one. Okay, so what is the limit as f of x, or sorry, what's the limit of f of x as x approaches 5? Okay, so here's 5. Ooh, that's a pretty color. Okay, so we approach it, and on this side, notice how it's approaching -1. Okay, and as I come from this side here, it is approaching 2. So notice how from the other sides they're not equal. So this does not exist. Now, is there a value at 5? And the answer is sure. Right here, I have a closed dot here. Okay, so when I plug in 5, my function is going to spit out 2. Okay, so for a limit to exist, the left and the right side have to equal to each other. So these are called one-sided limits, right? From the left or from the right. So we get these types of questions. And there's notation for this, which you guys are familiar with. We talked about this in Accelerated 3 last year. What's the limit as x approaches 5 from the left? Okay, so this says as x approaches 5 from the left. Okay, so what's the limit from the left side? Okay, and we said that was -1. So -1. Okay, and then similarly, right, the plus icon here, or not icon, the plus in the superscript is from the right-handed side, right? And this makes sense because negative numbers are on the left, positive numbers on the right, so that's the way I remember it. Okay, and from the right, I believe it was 2. Okay, there is, yeah, 2. Okay, so that is one-sided limits. Now, I brought up these examples up here. Notice how here my limit existed and the function was the same. Here the limit existed, function was different. So in order to have continuity, you need to be able to have the left and the right side limits to equal each other and the function to equal that value. So the simplistic idea about continuity, right, and kind of in the root word here, it's continuous. A function is continuous, or you have continuity, where it can be drawn without lifting a pencil. So if I'm just drawing something, okay, and I never lift my pencil, you have continuity. Okay. Formally, the definition is what I talked about, where its limit exists, okay, and the function value exists, and they are the same. Okay. We do have different types of discontinuities. We do have these 3 discontinuities. This is important, okay? So I would circle this one. We have holes, okay? We talked about holes last year. We have vertical asymptotes. We've definitely talked about those. And then we have jumps, which all 3 of these exist in our last example up here. Okay, so we're going to go through that example talking about example 13. It says list the x values of the discontinuities of the function y equals f of x graphed above. So if I look over here, and what I'm going to do, I'm going to get rid of these. Okay. So the idea, right, is can I draw this function and not lift my pencil? Every time I have to lift my pencil, discontinuity, right? Not continuous. Okay, so I'm gonna go ahead, sketch this. Notice here, right? I have a function output. Okay, so still continuous. Uh-oh, right here. Okay, so here's a discontinuity, right? I have to lift my pencil to jump over that hole, or to get over that hole. Okay, so I'm gonna go back to red. I'm gonna mark it right here. Okay, drawing. Uh-oh, another hole. Okay, then I get down here, and I go to infinity and beyond. Okay, but here I have an asymptote. This is also a discontinuity. So there's another discontinuity. Okay, picking up here, and oh, I have a hole, but then also this is what we call a jump discontinuity here, right? So this one's jump, and it's pretty easy, right? You jump, okay, you have a hole, or you have an asymptote. Okay, so those are the three types of discontinuities that you're going to see. So down here it says, what are the x values of the discontinuities? So what did we say? -1, 2, 3, and 5. X equals -1, 2, 3, and 5. Okay, those are your discontinuities. All right, okay, I'm almost done with this video. This says all discontinuities can be classified as removable or non-removable, okay? Non-removable discontinuities occur when the limit of the function does not exist, okay? It jumps or it's vertical asymptotes. So by that logic, right, removable discontinuities occur when the function has a limit. So it has a limit, just its function value is something else, right? Or it doesn't exist. So that would be a hole, okay? So removable is a hole. So I'm gonna write this here. I suggest you write this. Remove, I forgot how to spell. Removable equals a hole. Okay. So example 14 says, which of the discontinuities from 13 are removable? So we go back to our discontinuities here, and which are removable, or where do we have holes, essentially, okay? So we have one hole here. We have another hole here, okay? And yes, there's a hole here. However, this is a jump discontinuity. It jumps, right? The limit does not exist, okay? I have limits for these two holes, but this one does not have a limit, okay? So that's not removable. That would be non-removable, okay? So we can just answer this at x equals, that was, I believe it was, sorry, I got distracted for a second, -1 and 2. So x equals -1 and 2. All right, so that is it for this lesson. I'm going to pick back up. We'll talk about calculated limits algebraically, and we'll talk about piecewise functions in the next video. But remember, in this video, we talked about limits and continuity. Okay, so what does it mean to have a limit? And is a function continuous at a certain value?